So a little bit about me. So my background's actually in physics, but I kind of took a roundabout path and came to programming instead. So I've been working as a software engineer for about 5 years now, with the past 2 of those being at Holland & Hart, working pretty much exclusively in Haskell. So at my company, Holland & Hart, it's a law firm that has an office here in Boulder. We actually work on cutting-edge legal automation technology and AI platforms, with pretty much the entire backend is actually written in Haskell. We're hiring as well, so if you're interested, right now we're kind of looking for data scientists, but we're always looking for qualified Haskell developers as well. So if you're interested and want to work in beautiful Boulder, Colorado, come find me at any point during the conference. You can also reach out to me on the functional programming Slack, just at Keuhlen. So today's talk is going to be kind of broken up into a few different sections. So first, we're going to talk through each of the individual design patterns that make up an extensibly free arrow. So we'll talk through what extensible is, what are free structures, what are arrows, and then how do you put all of those things together into one superstructure. And finally, we'll talk about why that's useful and some cool things you can do from a high level that you can utilize this structure to kind of accomplish really interesting tasks. So first, we need to know what extensible is. So extensible really is, when you get down to it, is the attempt to bring closed types and turn them into open types. Closed types are those like algebraic data types in Haskell. So they're ones where if you want to extend the type at all, or to give it another constructor, you have to go and change the definition of that type. Now, it can be really cheap to add operations on those types. So a function that works over something that has a type, where it's an ADT, is really easy to define. But if you want to add a new type of thing inside of that ADT, you have to go to the definition, change it, add some new constructor, and then recompile all of your code. And that's not to mention that it may not even be possible for you to change the definition of that, because it could be locked in third-party software, in a library somewhere, or in some part of your code base that you're not allowed to touch. Open types are kind of the other side of that spectrum. So there are things like type classes in Haskell, where you can go and you can add a new instance of a type class anywhere, no matter where the definition is. But it gets really expensive if you want to add a new function for that type class. So again, you may not even have access to wherever that definition of the type class is. So extensible kind of tries to combine those two things by pulling together groups of other fully defined types. And extensible types try to solve the problems of both open and closed types by instead defining a minimal requirement for your functions, and then defining easy ways to lift into your extensible types. So easy ways to combine things, and then minimal requirements for your functions. So you don't have to worry about what other things are there, and how do I get to that kind of type. And when you add extensible constraints into the mix, they allow for more reasoning about what your types actually do. So as an example, we can kind of think about 2 different classes of extensible types. So sum types and product types. Now, sum types are just like ADTs, and the typical example of that is either. So something is either a left value or a right value. It's true or it's false, and kind of wrapping some notion of that. Product types are the dual of that, and sometimes you'll hear these things called products and co-products instead. But really, sums and products are kind of a better way to think about it, for most people at least. And the example type of that is tuples. So in a tuple type, you always have both of the constituent types there. So if you have a tuple, a string, and int, you always have a string and you always have an integer to go with it. So we can make these things extensible by defining a couple things here. And this is kind of an example of what the Haskell code would look like. And I'm sorry for the contrast here. I was hoping to get the front lights dimmed, but that isn't actually possible in this room. If it's hard to read, like I said, you can follow along with the slides online, and hopefully that's a little bit easier to see. So for sums, we can define an analogous thing and then nest all of our sum types together. So you define a left component and a right component. And as you combine more and more things together, you just keep nesting either left associative or right associative. So you may have a left, 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 and then a right value. And the way you kind of handle that is by abstracting away all of the actual formal structure, whether it's lefts and rights, and you just define a sum class that gives you a way to peek into your sum type, which, as you can see here, it goes from the larger sum structure, and you get a function that allows you to peek in and see, do I have something, an actual value of a certain type inside of it? And then you have a way to lift, which takes a smaller type and brings it into a larger sum class. And the third thing we're going to define for each of these is kind of just a type operator. And this is for the constraint side of things. So that when we want to say something has a sum class, we can define kind of a shorthand syntax that makes our code a lot faster to write and easier to read once you become familiar with it. So product class is the same thing. We're just going to use a standard tuple definition and then nest things. So you end up with nested tuples that you can chain together composition on to access anywhere in that structure. And again, we have analogous type class where we can grab something out of our larger structure. So in our early example, we had a tuple of string and int. You can say grab that integer, and it doesn't matter how arbitrarily deeply nested it is, it's going to return the first integer that it finds. Stash is a way to combine a product class, a value, and then kind of shove that value into your product class. So it allows you to do things like in-place modification like you would do with lenses as well. So extensible is useful in a lot of different places. A couple of them that come to mind are listed here. So heterogeneous lists are not actually possible to define in Haskell, but some types allow you to define a really quick wrapper type that allows you to combine, if you want a list that has strings and integers, you can just define a new type that is the sum of strings and ints, and then every value in your now heterogeneous list is kind of a left string or a right integer, and then an easy way to operate over all of those pieces. It allows you also to have extensions to type classes. So again, you may not have control fully over the definition of a type class or where it lives, but you can add another type class that is a kind of a subclass over an extensible type so that you can redefine what some of those things mean in your specific context. It also allows for type level programming, which basically means you can use the constraints to determine what your program is going to do. And you can do half of your programming at the type level, saying what are the things going to be in this function, and adds constraints on what the forms that they can take. And then write your functions half in the type level and then half in the value level to kind of give you some more powerful combinations of functions and prevent you from composing functions that really shouldn't have any business working together. They're also really useful when you have a complex and growing environment. So let's say you're working on, one example that I've given before is you're working on writing a simple game program. And you have a state, but you really don't know what things are going to be in that state because you haven't really figured out the entire complexity of your game yet. Well, as it grows, if you keep adding new things to your state, if you don't use extensible, every single place that you defined what that state was, so let's say you're just using the state monad, and you say, I have a state t int, and I'm just carrying around some number that represents game state. Well, when I want to add something else to that game state, I have to go through every single function and recompile it. When you use extensible effects, it allows you to say, I'm going to have just some state. I don't know what it is, and it's going to be some product class. I can then write functions that operate on just the first part of it and say, in that product class, I'm going to say there's an integer. I don't know what else is in there, but I know that at least there's going to be this one value, and then write your functions over that instead. They also provide a replacement for monad transformers. If any of you went to the coding F in Anger talk yesterday, they used the FreeA monad or FreeA simple package that uses extensible effects to do just that, where instead of defining it into a full monad stack, you just say that I have some type level list in that case, and then define constituent elements of that whenever you need them. You define the minimal set of things inside of your polymorphic variables, so they're the most maximally useful. So free, I think many of you were kind of in the talk right before this in here, where we talked about freeing all of the different kinds of things. And one way to think about free is really just the minimal definition of a structure. So it means that it's whatever structure you're freeing, the free structure is the one that barely satisfies the laws of that structure. So for the free monad, it barely satisfies the monad laws for maybe defining return and bind. And when I say barely satisfies, I mean that you don't have any other information besides satisfying those base level laws. It's just enough to kind of cross the goal line that, yep, this is a monad, and then you do nothing else. And the same way we can define free for all kinds of structures, as that previous talk kind of went through. And the cool thing about free is that it basically shows up anywhere where you have a set of defining laws, you can define a free structure. The really thing that you need is just to be able to define anything that meets some set of laws. And then you can kind of delay interpretation of more about that structure until later. And it's really cool that anywhere where you know that you have properties that you can kind of define, you can also define a free structure for that. So free is really a useful abstraction in its common usage for separating side effects from your programs. It allows us to program in a way that we think about really, separate ways of what is our program, and what effects do we have, and then what do those effects actually do. So if we think about these arrows as kind of marching through a program as you go on in time, a normal program might just mix through some I/O actions, a pure action, a state action, another pure action, and then I/O. With free, what you do instead is you annotate those areas where you might have an effect with just an effect annotation. And instead you say, I have a program now that has a mix of purity and effectfulness kind of mixed together. And at some point in the future, I will come back and tell you, what do those effects actually mean? What do they do? And how do we do them? Was there a question? I thought I saw a hand. Nope. OK. All right, so we're going to go through a totally hypothetical example that I swear did not actually happen to me, but it probably did, where on our system we send a series of automated emails. And that can be good and bad. And in this case, it was bad because we had just sent a set of automated emails to about 1,000 different clients outside of our company. And in the first place, this automation was never supposed to talk to anyone outside of the company. So it was bad on 2 different levels. So while looking into it, you trigger it again. And you just set the same automated emails to those same 1,000 clients again. And when you start looking into the code, you realize there's like 50 different places where you send emails. And it's hard to kind of pinpoint, especially in a flurry when you're trying to make sure that whatever triggered this automation isn't going to trigger again and do it for a 3rd time. So what's the fastest way to go through and make sure that you stop sending this spam? Well, if you're using a free structure, the easiest way to do that is to just change your interpreter, which is any place that you defined send an email, change what that means. So in our case, we had a free architecture that allowed us to have instead of I/O calls to some sendmail program, we just had an effect that we called sendmail. And that lived in multiple different places. We had a couple different interpreters for what that meant. But all we had to do was go in, adjust the interpreter for sendmail, and say, in this case, we kind of just remove all external email addresses. If we're going to spam people, at least spam people in our own company rather than our clients. So this really showcases where it's really useful for free. Because rather than having to kind of stitch through all of those different places in our code that we would have needed to redefine what it meant to send an email, we had really 1 or 2 places that we had to go in and say, this is what it means to send an email, and that is you're not allowed to automatically send emails outside of the company unless we pick a specific interpreter that we name in such a way that is send outside emails. And so you have to be very deliberate if you want to actually put together something that can automatically reply outside of our domain. All right, so arrows are something that a lot of people don't really have much experience with. And for me, they've actually become really natural because our entire architecture is based on these extensively free arrows. And so I kind of work with them every day. And for me, I kind of I struggled through the idea of why are arrows better? So I'm going to let someone else kind of explain that in more detail and really talk about places where I know that they're really useful, but I can't really tell you exactly when should you pick monads or when should you pick arrows, because for me the question's simple because I have an entire architecture built around arrows, that's the fastest way for me to solve any problem. But arrows really are a generalization of functions. So any arrow from some polymorphic type A to some other polymorphic type B is really just a function that takes in that input value and then spits out the output. And where they're really useful that we've noticed is anything that's time sequential in operation. So people use it to model circuitry, any kind of pipelines, whether that's human workflows or data data pipelines, anything that kind of has a logical time ordering to it. Arrows are a really useful way to model that program. And they're also useful in parallel computations as well due to some of the arrow laws that we can talk about a little bit later. So arrows can also be given additional type class instances. You can make them instances of applicative, functor, or bifunctor to kind of make custom arrows even more powerful than just the basic arrow type class. And what I think is really important to know when you're talking about arrows is that they add an additional layer of structure on top of computations. So when you're thinking about monads, you have some monadic value, means you just have, for some monad M, I have a value of type B. But with arrows, rather than just a context and a value, I have a context, a value, and a way to get that value. And that's really the structure of arrows that we like to exploit to build more powerful programs. So really, it's that input parameter that allows you to define your programs in a more powerful way. So Classically, arrows are the way that you kind of lift monads into an arrow. And in Haskell, because you have to, if you want to do any kind of actual I/O, you have to use a monad. So to do that, we kind of wrap our arrows in the Keuhlen I/O monad to kind of, it's a Keuhlen arrow, which has its own library. I think just control.arrow.Keuhlen in the package repositories, and then you can run those effects from the arrow structure. And when you start comparing, well, I have an arrow, a Keuhlen arrow, and their monad. A lot of people think that the arrow version is a lot less powerful, and that's because, well, one, you had to define this special Keuhlen arrow structure to kind of bring in the monad to begin with. But beyond that, you can't actually just use the arrow analogs of return and bind. So arrow defines three kind of main computations. So it has a version of return called error, which is just ARR, and that kind of lifts pure functions into arrows. It defines sequence, which, like bind, kind of composes two of these things together. But to replicate any actual monadic computations, you need an additional type class member called first, or it's kind of an analogous pair of second, which allows you to kind of perform operations over branches of arrows. And well, a lot of people think that that makes arrows less powerful. I think that they actually makes them more powerful because it allows you to write programs that are more specialized in specific ways. And again, it's this additional structure that allows you to write better, faster, and more correct programs from the get-go, rather than having to continuously think about just the values that you have and what you want to do with them. So free monads allow you to interpret or to create different interpretations of your effects. But free arrows allow you to interpret your programs entirely differently. And that's kind of just a teaser. We'll come back to that idea later on. So now we have all of the constituent parts defined. We can really build an extensibly free arrow. So again, this is a design pattern that takes bits and pieces of all of those different three components, combines them together into one single design pattern that's really powerful. And there's lots of different ways that you can go about defining extensible, defining free, defining arrow. But I'm just going to pick one structure using GADTs to encapsulate both arrows and our free effects. And if you've done any kind of free effects or freer simple programming, it's really the same kind of idea. So let's go through the definition. So for a free arrow, we can kind of define a free arrow that just has three pieces to it. We're going to have an effect that we're going to include on our arrow. We're going to have an input parameter, and we're going to have an output parameter. And the first thing that we need for our arrow definition is a pure notion. And this is how we get from pure functions and lift them up into our arrow structure. The next thing we're going to need is something for our effects, which is what does it mean to actually have some kind of effectful computation inside of our program. The next thing is we have to define what sequence means, and how do you sequence two of these things together. So it's really just function composition here. And then we're going to define a parallel piece. And this comes straight out of, or mirrors the arrow type class instances and how you would define them for anything. There's also additional, if you've done any work with arrow, you know that there's additional type classes beyond just arrow. So a couple things that you could add in there are things like arrow apply, fan in, or split, which come from the arrow apply type class and the arrow choice type classes. You could also do this kind of structure if you wanted to use it for functional reactive programming where arrows are typically used by defining an arrow loop instance as well. So there's other kind of arrow type classes you can fit in here, but I just kind of went with the basic definition. So the first thing you have to do is you have to make your new data type a category so that we can do function composition on that. And this really just defines identity and then the dot function composition. And then we can actually define our arrow instance. So here we're going to define for the type class error, we're just going to make that our pure data type. First is just going to be a function applied over the first piece of a parallel arrow. Second is, again, the second piece of that arrow. And then the last piece is just kind of the arrow parallelization, which is that triple star. So now we can look at what happens when you build arrows. And this is kind of standard arrow syntax. So you have one arrow kind of sequenced into another arrow that is parallelized. So the triple greater than is sequence, and then the triple star is the parallelization from control.arrow. And when you define your arrow in this kind of structure, it allows you to think about your programs, basically any program that you would write, as a tree. So here we have our first effect of just some arrow is sequenced together with another parallelized arrow, where every single leaf in this tree is going to be actual computations you're performing. Those might be pure computations, they might be effectful computations, but all of the nodes or the leaves of your tree are where your computations take place. And all of the higher level nodes are all of the structure of your program, Where do the breaks, the different control flows that you have kind of installed? So like I said before, free effects can be interpreted into various real effects in multiple different ways. And they allow you to separate the representation of your effects from how you actually run them. In the example earlier, again, it's how you go from just the idea of sending email to what do we actually do when we send an email. But that's really not the right language that we kind of came up with when we were building our architecture. We really think that there's something more that we do with free arrows rather than just interpret them. And so we kind of look for something else. And for us, that's what we call compilation. So compile is to produce by assembling information from collected from other sources. And free arrows really, we argue, are better thought about as compiled into different things rather than just interpreted. And there is an interpretation step because you do have free effects in there. But your arrows as an entity are compiled down to mean different things. So because of that additional input structure, we can think about our arrows as having this idea that you can separate the representation from your program from the running of your program. So we can build up an entire purpose of an arrow that says, we're just going to use this to send email. And then later we can determine how does that thing actually get run. Not only what do the effects in it mean, but what do we do in all the different places where we want to actually make calls to the CPU to perform some operations. Okay, so when you define free effects, you kind of go through building it up here with just a GADT again. We just define an effect that has an input parameter and an output parameter, and then we define members of that data type for our print x, and the kind of x suffix is what we use to denote effects in our code. So it has one kind of effect notion, and that's just going to be print for us, make something really simple, and then we define two interpreters for what it means to print. And these can be really, really simple things. In this case, we're just going to say whether or not you take a text and just like print it to the screen or whether printing means to a file. But if you've never worked with free before, this is kind of where it really starts to shine. Because anywhere that you have this print idea, if you want to change the entire semantics of your program and say that rather than printing to some log file, we're going to print across a WebSocket to some aggregator source, that becomes just a single place where you change your interpreter. So these ones are really just going to be baked down to Keuhlen to kind of perform some I/O action. But you can define effects that are much more complicated and depend on other effects inside of your code. And we'll kind of come back to that a little bit later as well. So here's what a compilation step would look like for arrows. And this is a really simple one that does the basic level computation. So the first thing you would pass in here is some function that defines a way to get from your effects to an actual arrow. And then you pass in a free arrow, and you get just a regular arrow at the end of this. So this is just defined with a quick recursive function that goes through and says if you have anywhere where you had pure, just make that into the typical arrow type class, arrow to kind of lift it up. You can kind of define just the standard arrow function composition for sequencing and arrow parallelization. And then for effects, you just kind of use that function you passed in that goes from effects to arrows to kind of define these things away. And this is the step that you would kind of decide what does compiling actually mean. And you can change any one of these definitions to do something slightly different. So we also needed one more step, which is something that can evaluate a Keuhlen arrow. So all of our things are wrapped in so our free kind of goes down to an interpretation of a FreeA with some Keuhlen M inside of it. And so we need something that kind of unwraps our free layer and then turns it just to the Keuhlen so we can call run Keuhlen to actually run code at some time. So here we kind of just do the same kind of thing we did with compilation, but just specifically going from an arrow or free arrow with a Keuhlen effect down to just a Keuhlen arrow instead. And then at the bottom there is a lift k is just kind of this way to take some monadic function and lift it into our free Keuhlen arrow. And that's just kind of a helper function to use along the way. All right, so now we need to kind of introduce the extensible portion of our arrow. So just like we defined a pretty simple sum and product earlier, we can define a similar higher kinded sum type here. So this one, which has something either in the left component or in the right component, is really analogous to the one we saw earlier, with the only difference being we have an input parameter and an output parameter as well. So this allows us to think about our effects, which are going to have some input type and an output type, and turn those things into a extensible effect along the way. So we kind of define just two pieces here, which is just what the base definition is, and then a type operator that, again, we kind of use to make our code a little bit easier to read. But that sum2 is just the same thing as sum class, but again, with higher kinded notation. And then we define a way, a lift-f, which again is lifting from some specific effect into the higher sum class type effect. And then on the right-hand side, we have a function that kind of maps our effects between each other. So you pass in something here, a function that goes from an effect 1 to an effect 2, and then you can take an arrow of type effect 1 to arrow of type effect 2. And this kind of allows us to lift all of our arrows together, or lift our effects into some higher sum class, and then combine and compose our arrows no matter what effect they actually have. So here's where we would actually use something like this. And this is a really simple example where we have two arrows now, and all they do is they call their effect for print, and then we've defined off screen another effect for storing things, whatever that means. So the way our definitions look in pretty much all of our code base is pretty similar to this. So the first piece is, if you're not familiar with Haskell, is a constraint. So we say print A has a type where a polymorphic effect is constrained to be a member of the sum, be from a sum class that contains print x. And the type of printf totally is a free effect with some polymorphic effect with that constraint that goes from a text and then just has a unit, kind of a void output at the end of it. And similarly, for our store, we're just going to say it's the same kind of thing, but maybe for whatever reason, we work on strings there and text when we print things. Now we can take those two pieces and combine them into a single extensible arrow that uses both of them. And this is really simple, so you can actually write it a lot shorter than the way I did here. Oh, it doesn't go away. But I wanted to kind of show that if people aren't familiar with it, arrows actually come with their own version of do syntax called proc. And proc notation allows us to write things that are kind of complicated in how I want to pipe my arrows together. It gives you some syntactic sugar the same way that monads have the do syntax, so that it's a lot easier to think about pieces, and you don't have to just see those kind of 3 asterisks for parallelization all over the place with the triple ampersands for fanning together functions. You can write arrows that way, and that's where a lot of people see them. And those are kind of the pieces that people typically pull out for writing just regular functions. But they can be hard to understand exactly what they do. And so I'm kind of a fan of proc syntax, which is just that syntactic sugar that allows you to be a little bit more explicit about what's happening and define your control flow a little bit more controlled way. So you'll notice here that our constraint grew from 1 piece to 2. And that's really helpful when you're programming, because it allows you to have kind of your top level arrows just be composed of smaller ones. And if you accidentally introduced an effect, like let's say we threw in a third effect here, our program just wouldn't compile. You can't accidentally pepper in effects, and you have to be deliberate in your constraints to make sure that your programs are doing exactly what you think they're doing. So here we kind of are explicit in that we work with whatever our effect in our arrow is, it has at a minimum a print and a store. And if we tried to use anything that wasn't one of those things, those two effects, then our minimal definition would have changed, and GHC just wouldn't compile our code. So what this allows you to do is really write isolated algebras for your different tools. So it lets you think about your business logic in separated domains and then combine those things for your full programs at the end of it. And then it makes that really easy to do, because you can just define arrows that are maybe as simple as just print and store, and then piece those together with different data pipelines to say, this is what we're going to do in this context versus some other context. But it allows for really reusing pretty much all of your code base and all of your business logic for different things. Like, what does it mean to talk to your database? You can define that in different contexts and then just kind of pull in your database arrows whenever you need them. So one of the downsides is that when you actually want to run your arrows, it can be kind of messy. And this is what it would fully look like to actually run that simple arrow that I ran, that I showed you before. So at the outside of it, you have to call run Keuhlen from control arrow Keuhlen with some input, which is that final text thing on the right, or the far bottom right-hand side. And then you have to stitch together in the inside a call to eval Keuhlen to kind of unwrap your Keuhlen piece, a compile for turning your free arrow into an actual arrow, and then interpreters for your free effects as well. And this is one of the parts of our system that we've kind of been struggling against, because when you're working in GHCI, it can be really difficult to kind of actually like run in Arrow. You can't just call it and it operates, because it's peppered with all of these different effects inside of it. So we've worked really hard on making this kind of step easier in lots of places by kind of throwing away this boilerplate and defining easier functions that kind of just run our arrows. But at some point, you're going to have to write kind of messy code to go through all the different pieces. But I'd say it's a pretty good price to pay when just running your code can be messy here, but everywhere else where the logic actually exists can be a lot cleaner. One other thing that a lot of people forget about is that you do have to pick an order for your effect type at some point in time. And here we kind of implicitly picked it with the order that we kind of chained these operators together in, or the interpreters together. So in this case, we would have had a print effect on the left and then a store effect on the right. And we kind of had to say what that order was going to be, just because GHC does have monomorphism restrictions. But that's not really important here. So where do these things really shine? Well, first off, I think any place that you're using arrows, I think it makes a lot more sense to use free arrows instead. And these extensibly free arrows are kind of the best of all of the world in monads, of whether extensible effects or free monads, and kind of combining all those things together. We use the same kind of notions in this extensibly free arrow, but in a lot more powerful way. So anywhere that you're already using arrows, I think makes a lot of sense to use these instead. Again, free allows for that kind of maximal use of what we call operation algebras. And that's just, what does the business logic actually mean in different places? What does it mean to talk to this microservice or that microservice? What does it mean to kind of interact with our database? You can reuse all of those pieces in a really simple way. And so anywhere in your code base, you can go in and say, oh, this is a database effect. Cool, I know what that does. And then extensibility makes it really simple to pull together lots of arrows and to make sure you're doing it in a correct way without introducing accidental side effects. And then the structure of arrows, like I mentioned before, allows for a lot of other fun abstractions. So last year, one of my colleagues that I worked with to kind of build up this architecture gave a talk on how to program like a 5-year-old in Haskell. And what he was really getting at there is something that we've talked about a lot and we use in our code base called arrow assembly. And what this does is, because arrows have an input parameter, we can think about what do programs just look like that are assembled from all kinds of arrows. So we can have just a big list of all of the different arrows that we use to get from type A to type B, and then piece together all of the possible paths from those components to go from, say, unit to text. And we define lots of new types throughout all of our code so that it makes a lot of sense stitching together how do you get from a specific kind of thing to another specific kind of thing, so we can build programs that are really general. I'd encourage you, if you're really interested in this idea, to take a look at this talk on YouTube from last year. So another place where the structure becomes really useful is when we're wanting to know what parallelization means. So in this case, we're kind of going to bring up our tree from before. And we have one piece here that says parallelize some pure piece with some effectful piece. Well, in your compilation step, you can radically redefine what it means to be parallel. So here, it might mean that you're going to just have 2 different green threads that are running different things, but you have total control over that when you compile your arrow. So for whatever reason, you can say that those effects really need to happen sequentially. So when you're actually running it, I want you to do the first effect, the pure, and then the second effect. Or you can say, I want you to run those different pieces on separate servers entirely. I want one computation to run here, one computation to run there, and just kind of redefine what your program looks like. And this allows you to have full control over not just what your program does and what it means to have effects, but how your program is run on actual machinery. Another place where this is useful is in optimizations. You can kind of look over your entire free tree of all of your arrow operations, and then you can search for known bottlenecks. So let's say that I have 2 effects that I know about, and any place where those 2 things are sequenced together, it's slow. So I'm going to define something that is the combination of those 2 effects. And then any place where I see them in my program, I'm just going to replace them with a faster one. So now I don't have to think about what's the fastest way to write my code when I'm putting things together and chaining effects, and what's going to happen when I sequence 2 effects together. I can defer that kind of intuition until later and say at the compile time for my arrow, I want you to do something different, and I want you to do something special in certain cases. And one place that we think that these really shine is that you can use shared interpretation of your different effects. So this is just a simple picture of what we would call a compiler lattice, where you might have different effects in your arrows, and they're going to, like I said before, you can build them on things other than I/O, right? I can define a database operation algebra and say that that thing actually is built on top of some REST layer, where REST is some effect that we define for talking, HTTP verbs to other things. And then we have two microservices that are also talking REST to talk to their various components. And I can just define in one place what it means to be a REST effect. What does it mean to actually make a GET request or a PUT request and to deal with the responses as they come back and deal with all of the error handling that entails. So what a lot of our code actually does is we compile down finally to a specific error effect that we've defined and then a Keuhlen I/O. So that lets us get exposed to all of the power of the I/O monad at the end of time when we're running our arrows, as well as full control over every error that has ever happened in our program. And because of the shared interpretation, we don't have to think about in the database level, what happens if REST decides to give up? What happens if our network disappears out from under us? We can leave all of that kind of error handling to the REST layer and use it there instead. So these things have a really formulaic use when you're working with extensible arrows. And the first part is just determine what are your operation algebras. And then you're going to sit there and you're going to what we call joust with the compiler until everything finally unifies. And you'll notice that that's a common theme here because GHC really guides you through the process of putting together your programs. And it's, again, a lot of people say in Haskell that if it compiles, it works is kind of a common idiom. It becomes especially true when you're using something that has these polymorphic variables with specific constraints because you cannot put together programs that are incorrect in the types. You're doing half of your programming at the type level and then half at the term level, so you can just basically throw things together and know that it will work. You do the term programming in one place, and you don't have to think about how they're going to fit together because when it compiles, it works. So the second thing is you're just going to write your extensible arrows that kind of use that operation algebra and any kind of logic that needs to go into them. Then you combine all of those extensible arrows into programs. You compile those arrows from whatever that means to be the arrow that you built into the real program, and then you run that thing. And that's kind of how you get through the entire operation of the day-to-day work that we do at our company, is we go, anytime we have a new project, we think about what are the operation algebras we need to use. Is this going to need a database? Is it some new microservice we have to interact with the API for? We'll write all of the arrows that kind of iterate or utilize those algebras to think about the business logic that's going to go into the data that's coming in and the data that's coming out. We combine them into the full program, compile it, run it, ship it, we're done. So a couple of final thoughts. Extensible free arrows kind of combine all of the utility that exists in free monads and extensible effects kind of together into one superstructure. And again, it kind of gives you a lot of additional power because of that input parameter that arrows carry around. And they can be painful at the final stage, but for the most part, you're not really going to spend any time there. You kind of write what it looks like to finally run your arrows once, kind of forget about it because you're just going to keep reusing that function all over the place to compile. And you just think about, what does my program need to do? How do I want to compile it? And what are my interpretation of my effects? And again, free monads are interpreted, but we kind of say that free arrows can be compiled into various different programs. So that was kind of a whirlwind through the world of extensibly free arrows, and I'm happy to kind of answer any questions that you all may have. Yeah?
What do you mean free monads are interpreted? Can you get into more details?
Yeah, let me go back to there we go. So the first place here, when in a normal program, you kind of just have I/O actions or other monadic actions. But when you have a free program, especially with free effects, the interpretation means somewhere in my code, I have decorated something that is an effect. Interpreting that effect means wherever you see that annotation, replace it with the real I/O action, whatever that is. So when you're working with free effects, you're really just building an annotated data structure. And then interpretation is finding all of your annotations for specific effects and then replacing them with what they should really do. So in the context of our free arrows, we did that in one place. So here, we define a free effect for printing something. And then I defined two interpreters for what printing means. So interpret print could just be literally call, I put string line, show it on the command line, put it out to std out. Or it could mean I want wherever I said print things, put it in a file instead. So interpretation is really changing what it means to print something. Does that make sense? Okay. Yeah.
I have a historical comment.
Sure.
Keuhlen was a Swiss mathematician in category theory. He apparently died in 2011. Had a very strong career, especially many people in category theory. If you search in Wikipedia for Keuhlen category, then it also gives you links to his own page there. So he would be astonished that his name was being immortalized.
Well, it's not just in arrows either. It's also, there's an entire notion of Keuhlen composition in monads as well. It's not just the arrow piece, but it's, you're right, he's kind of immortalized in functional programming because of his working category theory.
Absolutely, yes. English is a treacherous language, especially with vowels.
Yeah.
I just wanted to
Thank you. Yeah.
So, okay, so future state. I've implemented my stack using extensively free arrows. The interpreter is done. So all the plumbing and all of the one-time work is done. And now we're just building business logic.
Yep.
Using this. Is there like a style guide or something that we can follow or come up with something like that? Because we have used arrows in the past, and because they give you combinators that then map the input at later stages and stuff like that,
Yep.
we've seen that sometimes, like especially for new people, it's resulted in unreadable code because you start with an arrow and you do 4 things its output.
Yeah.
Somewhere in the middle, there's like, oh, okay, by the way, map the input for this thing. So it's very hard to reason about like where did that happen and what the flow is.
Yeah, so just to kind of give everyone else an example of what he's talking about. So arrow kind of defines at the base level a couple of these different combinators. So this is kind of the parallelization one. This is fan out, which kind of copies an input over 2 functions. There's other combinators as well. So sequencing, pure sequencing. You can do it right to left or left to right. You can, there's an arrow 0 kind of type class. There's these additional ones for splitting input and fan in. And I think you're exactly right. When you start combining all of these different arrow operators, you can write really concise, what some people might call clean code, but I think it's unreadable garbage for the most part. I think the same way when you're using just monad bind all over the place, it can be really confusing to what's going on. And that's exactly why do syntax exists for monads, is that it's a lot easier to think about the control flow when you just kind of go one line at a time going through the program. So for arrows, I think since we have proc syntax that kind of replicates that do syntax, it's much better for writing readable code, especially for new programmers, to go through and use just do the proc syntax, think about it one line at a time, and then you might duplicate some things, and you could definitely make it more concise later. But don't worry about that for the first iteration, because the compiler is going to actually do a lot of the optimization for you. And if you had 2 lines that really should have been a fan out, it'll combine them into the more efficient form because it's just syntactic sugar anyways. So I'd say probably avoid these operators is my kind of best practices in a lot of places. I really don't use fan-in or parallelization in most of my code. At most, I will use, you kind of have to use sequencing to kind of push together lots of arrows for quick one-liners if you're doing something simple. But otherwise, proc syntax is kind of the best way to go about that. And then fan-out can be useful, again, just like in very small one-liners. But if it's going to be anything more complicated than that, I like to use proc syntax to make it much easier for not only new programmers, but for me 6 months from now, knowing, oh, I was so clever back then, but I can't read it now, so it doesn't really matter. Yeah.
When you use the proc syntax, does that become a sequence or a parallel? How do you do it so that you explicitly want a parallel?
So I forget the exact rules, but GHC has its own set of kind of rewrite rules, like it does for do syntax with monads, where it can combine things in different ways. I forget exactly how it works, but I think if you use 2 arrows, if you kind of
is this similar to like the applicative do extension?
I haven't worked with that one, so I'm not 100% sure. But I can show you in the example we had. So in this particular case, where we had two arrows that kind of just were separated, this would be optimized probably to a fan out and an uncurry. But if they depended on different inputs, so like you have two inputs coming in, it's going to apply them in parallel. So I don't know the exact rewrite rules, but they do exist somewhere on the Haskell wikis that tell you what's going to happen. But it will figure out the right thing to do because if you go back to our definition, you only have kind of sequence and parallel, and it's just going to figure out that those two things happen in parallel, and you don't sequence everything because the types won't line up if you tried to sequence everything. So GHC can take advantage of the arrow structure as well for making nice syntax for the complex programs. Yeah?
So I'm trying to develop an intuition for the arrows, and I feel like I have a good intuition for applicative. And you mentioned that with arrows you have access to inputs. I'm wondering what's an example of something you can do with arrows that you can do with applicative?
So assembly, I think, is one of those things that we've kind of been working through as kind of the perfect example, is that applicative and monad both have the same kind of idea that you only really have values. You don't have the way to get those values. And so we kind of use that aspect of it, where anywhere where you need to think about what are the inputs to my program, arrows make a lot more sense there. To be honest, we actually, for our, this is not what our definition looks like. Ours is actually based on recursion schemes for some optimizations. This is kind of just a simplified example of that. But if you, most of our code, when we don't need to think about what the inputs are, we actually just use applicative syntax over our arrows. So we use applicatives over the arrow, and that kind of just becomes a nice structure so that all of our architecture is uniform. But then you can kind of throw away the arrow part if you really don't need it and just go back to applicative as well. So. Any other questions? All right. Thanks for listening.